You know that feeling when you walk into a room to get something and suddenly you're just standing there?
Staring at a blank wall.
Yes. Staring at a blank wall, completely forgetting what you were even looking for. Like you try to retrace your steps in your head,
Yeah.
but the original purpose of your trip is just gone.
Right. Yeah, it's that universal human experience of, well, a working memory failure. You had a specific goal, you took physical action to achieve it, and somewhere along the way, the context just sort of evaporated from your active thoughts.
Exactly. And I mean, we expect that from ourselves, right? We are human. We get distracted by a phone notification or, thinking about what to make for dinner. But you wouldn't expect that from a state-of-the-art artificial intelligence.
No, you definitely wouldn't.
Like you would assume an AI that can process thousands of words a second wouldn't just walk into a digital room and forget why it's there.
You would certainly think so. But it turns out, highly intelligent language agents get completely lost in the exact same way. I mean, when they try to solve complex, multi-step problems, they suffer from their own version of, staring blankly at the wall.
It's wild. So, welcome to the Deep Dive Learner. We have a really fascinating mission for you today. We are unpacking a state-of-the-art paper on generative AI by an independent researcher named Ning Liu.
Right, and it's called Track, Rank, Crack: Epistemic Working Memory Scales Multi-Hop Reasoning in Language Agents.
Quite the title.
Yeah, it sounds highly technical, but the core idea actually challenges a lot of the current thinking in the tech sector right now. It explores a framework called SLEUTH.
The SLEUTH.
Right. And what this research proves is that making an AI smarter isn't necessarily about giving it, more raw computing power.
Or training it on billions more parameters.
Exactly. Or building bigger data centers. It's really just about giving the AI a structured way to organize its thoughts as it works.
Okay, let's unpack this. Because before we can understand the solution, we really have to understand the problem here. Like, why do these incredibly advanced AI agents fail in the first place?
Well, the paper focuses on what's called multi-hop reasoning.
Right, right. So for the learner, a single hop question is simple. Like, what is the capital of France?
One hop, boom, Paris.
Boom, Paris. But a multi-hop question requires 3 or 4 logical steps or hops to actually get to the answer. You have to find fact A, which leads you to search for fact B, and then that gives you the clue to find fact C.
Yeah, and standard AI agents generally rely on a framework called REACT for this.
REACT?
Right, it stands for reasoning and acting. And the way REACT works is by interleaving a thought, an action, and an observation.
Okay, so how does that look in practice?
So the AI thinks, I need to find this specific thing, and then it takes an action like running a web search, and then it observes the raw text of those search results.
Got it.
And on 1 or 2 hops, this thought-action-observation loop works perfectly. But as soon as you push them to 3 or 4 hops, their performance just degrades sharply.
It falls off a cliff.
Completely. And the paper identifies 2 main failure modes for why this happens. The first being what Liu calls context dilution.
Context dilution. It sounds like, I don't know, watering down a drink until you can't taste the flavor anymore.
What's fascinating here is that is a highly accurate way to visualize it. I mean, when an agent using the REACT framework searches for clues, it generates and consumes text. Every tool it uses, every search result it gets.
Every internal thought it has.
Yes, every internal thought adds to its context window. It's building this massive, unstructured mountain of text.
Oh, wow.
So by the time it reaches step 3 or 4 of a really complex problem, the early discoveries, the crucial facts it actually prove in step 1, literally get buried under all the new information it just pulled in.
It just loses them.
Right. The agent loses track of what it has already proven because the signal-to-noise ratio has just plummeted.
Okay, so if I'm understanding the mechanism here, it's basically like falling down a massive Wikipedia rabbit hole.
Oh, totally.
You start with a simple question. You open 20 different tabs to research the topic, and by the time you're reading that 20th tab about some, I don't know, obscure historical event of the Byzantine Empire.
You have completely forgotten the original question.
Exactly. You've forgotten what you were trying to answer in the first place. Your working memory is just flooded. But let me push back on this a bit.
Sure.
These models process vast amounts of data instantly. They literally have the entire conversation history sitting right there in their context window. Why can't they just, remember the earlier tabs?
Well, the distinction really comes down to the difference between explicit and implicit state.
Okay.
For a standard agent, it's investigative state. What it knows, what it suspects, what it still needs to find, only lives implicitly in that growing context window.
It's just a transcript.
Exactly. It's just a raw, running transcript of everything it's done since the prompt started. It has no architectural mechanism to separate the signal from the noise.
Right.
So to an AI predicting the next token, 50 paragraphs of raw text is just a flat landscape. It can't easily distinguish between a verified, crucial fact it found 5 turns ago and a random piece of distracting trivia it literally downloaded 2 seconds ago.
So it's not that the information is technically gone from its memory. It's just that the AI can't prioritize it anymore.
Precisely.
It's basically drowning in its own messy notes.
Yeah, and that flooding effect is what triggers the second major failure mode, which is honestly even more counterintuitive. It's called the evidence sufficiency problem.
Ah, the certainty trap. I found this part of the paper incredibly counterintuitive.
Oh, it's wild. The researchers found that even when standard agents actually find all the necessary clues to answer a 4-hop question, like the facts are sitting right there in the context window, they often refuse to commit to an answer.
Wait, really? They have the answer, but they don't say it.
Yeah, they suffer from severe information paralysis. Because they can't explicitly track that they've solved steps 1, 2, and 3, they just keep verifying. And verifying.
Oh, man.
They exhaust their entire action budget on redundant searches for things they have effectively already proven.
So they just keep looking for more evidence until the clock runs out and they time out.
Basically.
So they have the answer, but they lack the internal confidence to synthesize it and say, here it is.
Right, because in a bounded computation setting where an AI only has, say, a certain number of turns to reach an answer, knowing how to search is really only half the battle. Knowing when to stop searching is just as critical.
Wow.
Without a structured way to evaluate what they already know, standard unstructured agents default to more searching. They choose exploration over exploitation every single time.
Okay, so we have two massive bottlenecks to solve. Learner. Context dilution, where the AI drowns in unstructured information, and information paralysis, where the AI gets stuck in a loop of endless verification.
Which brings us to the solution.
Right. If the problem is a lack of cognitive structure, the logical fix is to give the AI a structured way to take notes. And this brings us to the core of the paper, the SLEUTH framework.
Yes. SLEUTH stands for Structured Layered Evidence Updated Tracking of Hypotheses.
Quite a mouthful.
It is, but the beauty of this framework is its absolute elegance. It does not require any extra model training.
Wait, no fine-tuning?
No fine-tuning, no complex, expensive architectural changes to the underlying LLM at all. It is implemented entirely through prompting.
Just giving the AI a rigorously better set of instructions. I love that. I was visualizing it as, taking that chaotic Wikipedia rabbit hole and giving the AI a literal detective's notepad.
That's a great way to look at it.
Instead of just a messy transcript of everything that happened, SLEUTH forces the AI to maintain a strict 3-part epistemic working memory after every single action it takes.
And that tripartite structure is the mechanical secret to the entire paper. Let's break down the 3 parts.
Let's do it.
First, you have confirmed facts. These are verified statements, and crucially, they must be grounded to specific sources the agent has reviewed. Furthermore, they are monotonic.
Okay, monotonic meaning once a fact is written down, it's permanent.
Exactly. Once a fact is confirmed and written in this first section of the working memory, it is never deleted within that episode.
Period.
Period. This directly neutralizes the context dilution problem. No matter how much noise or distracting text the agent encounters later in its search, its foundational proven facts are preserved right there at the top of its state, clearly separated from the raw search results.
Okay, but I have a critical question about that mechanism.
Go for it.
If the confirmed facts can never be deleted, what happens if the AI extracts a fact early on that is technically true, but contextually misleading for the broader question? Doesn't it get stuck? Like it writes it in permanent marker on the notepad, and then it can't erase it when it realizes it went down the wrong path.
That is a very sharp observation, and it actually addresses a limitation the paper calls fact entrenchment. They provide a highly illustrative example of this, too.
Oh, perfect. What is it?
Imagine the AI is looking for a specific target city. During its early search, it confirms the fact that a specific historical figure worked in San Francisco during the gold rush.
Okay.
That is factually true, so it locks San Francisco into its confirmed facts.
But the question might be leading somewhere else entirely.
Precisely. It turns out the actual reasoning chain required knowing that this same person later founded Sacramento, and Sacramento was the target city.
Oh, I see.
Because the AI entrenched San Francisco as the primary location early on, it risks getting stuck searching for cities bordering San Francisco, completely missing Sacramento.
It put the blinders on itself because of its own permanent ink. So why doesn't this break the whole framework?
Well, this is where the brilliance of the second layer of the notepad comes in. The second layer is active hypotheses. These are the candidate answers the AI is considering, and they are ranked by evidentiary support. The agent explicitly assigns them confidence levels high, medium, or low, and links them to the confirmed facts that either support or contradict them.
Oh, like a detective moving the red string on the corkboard as new evidence comes in.
Exactly like that. The hypotheses layer acts as a safety net for fact entrenchment. Even if the San Francisco fact is permanent, as the AI continues to search and comes up empty on cities bordering San Francisco, its confidence in that specific hypothesis drops.
From high to low.
Right. And this drop in probability forces the AI to look at its other notes and pivot its strategy, even while retaining the initial fact. It basically self-corrects.
That makes perfect sense. The facts are permanent, but the interpretation of how important they are is completely fluid.
Yes.
And that leads to part 3 of the notepad, which I think is honestly the most vital part, open questions.
The open questions section is the engine of the framework. The agent lists the specific uncertainties that, if resolved, would most change its hypothesis rankings. And here is the strict operational rule. The agent can only take an action like executing a new web search if it is directly tied to answering the highest priority open question.
It grounds the action entirely. It stops the AI from just randomly Googling keywords because it's confused. Every single search has to have a specific justification tied to a stated open question.
Exactly. It creates a tight mathematical coupling between the epistemic state, what the AI explicitly knows and doesn't know, and its action selection.
This 3-part notepad is fantastic. It organizes the evidence. It prevents context dilution. But, learner, you might notice it doesn't actually solve the second problem on its own.
The information paralysis.
Right. The AI now has beautifully organized notes. It has its facts and hypotheses ranked, but it still might just stare at the notepad and refuse to make a final call.
Yeah, the working memory structure gives the agent the capacity to reason better, but it still requires a stopping criterion. It needs an external mechanism to break the certainty trap.
And the researchers solve this with a concept they call a nudge.
Right, a commitment mechanism.
So how does the nudge work?
The system imposes a hard rule that triggers when 2 specific conditions are met. First, the agent must have consumed a specific fraction of its turn budget.
Okay.
Through extensive testing, they found the mathematical sweet spot is 70%. So if the agent has a budget of 20 total turns to solve a problem, the nudge hits precisely at turn 14.
Wait, so at 70% of the way through its allotted time, why 70%? Why not nudge it at halfway? Or, wait until the very last turn?
It really comes down to the balance between exploration and exploitation. If you nudge the AI at 50%, it simply hasn't explored enough of the problem space.
It hasn't gathered enough raw material.
Exactly, so it will just hallucinate an answer. But if you wait until 90%, it has already wasted valuable compute time on redundant looping searches.
Oh, the certainty trap again.
Right. So 70% is the mathematical tipping point where exploration yields severely diminishing returns, and the agent needs to be forced to pivot to exploitation, synthesizing what it has.
And what was the second condition?
It must have gathered at least 2 confirmed facts. It needs a minimum threshold of actual evidence.
Okay, so it has 70% budget used and 2 facts confirmed.
Yes, and when those 2 conditions are met, the system literally intercepts the agent's thought process and says, synthesize an answer from your facts and hypotheses right now. Stop searching.
Here's where it gets really interesting, because this is the data point that really upends the current industry consensus.
Yeah.
You might think, well, the nudge is doing all the heavy lifting here. If you just force an AI to answer, of course it will stop looping.
Right. But the researchers ran a crucial control test.
Let's talk about that.
They applied this exact same 70% nudge to a standard unstructured React agent. They basically yelled, time's up, make a choice at turn 14 without giving it the SLEUTH notepad.
And what happened to the standard agent?
Almost zero improvement. It bumped performance by a statistically insignificant 0.2 points.
Ouch.
The unstructured agent just panicked. It guessed randomly or completely failed to synthesize its messy context history into a coherent answer.
It perfectly tracks with the detective analogy. Like, if you yell, time's up, make a choice, at a detective who has a completely messy desk covered in hundreds of random, unorganized papers.
They can't quickly summarize what they have.
Right. But if you yell, time's up, to a detective who has a beautifully organized evidence board facts here, hypotheses here, missing links here. They can actually look at the board, read the narrative, and solve the case.
If we connect this to the bigger picture, the profound takeaway for AI design is that a commitment mechanism is completely useless unless you have an organized epistemic state to synthesize from.
Because when they applied the 70% nudge to the SLEUTH agent,
Performance jumped by a massive 4.0 points. The structured working memory is the necessary substrate. The nudge just acts upon it. You cannot force a logical decision if the underlying knowledge isn't structured to support one.
that is such a powerful mechanical insight. Okay, so we've got the theory, we've got the framework. How well does this actually work in practice? We really need to look at the scoreboard here.
Let's look at it.
The paper ran SLEUTH against 5 established baselines, including React, Self-Ask, and Reflection, across heavy-duty datasets like Hotpot QA and music.
And to understand the result, it helps to understand why these data sets are so brutal. Hotpot QA requires an agent to pull facts from multiple disparate Wikipedia pages and combine them logically.
Right.
Music is even harder. It is compositionally designed to foil agents that just try to string keywords together. It requires strict sequential deduction.
And against those brutal tests, how did SLEUTH do?
SLEUTH dominates. But what is most important for the future of AI architecture is where it dominates. On easier two-hop questions, SLEUTH beats the best baseline by about 4.7 points.
Which is a solid, respectable win.
It is. But as the reasoning gets harder, the gap widens exponentially. On 4-hop questions, SLEUTH beats the strongest baseline by 11.9 points.
11.9 points on a highly competitive benchmark is huge. It proves that the advantage of structured working memory scales directly with difficulty, right? Like, easy problems can be brute forced with raw compute, but hard problems require cognitive organization.
Exactly. And the paper provides a real-world trace, a step-by-step log of how the agents tackle a specific 4-hop question that perfectly illustrates this difference.
I call this the Mario Andretti trace.
Yeah.
Learner, just listen to the complexity of the question the AI had to answer here. Who won the IndyCar race in the largest populated city of the state where the performer of Ningus Plays Piano is from?
Just holding the syntax of that question in my own head is difficult.
I know. It requires 4 distinct sequential hops. You have to trace the album to the performer to their birth state, the state to its largest city, and finally the city to the race winner.
So let's look at how the standard React agent handled it. It starts off okay. It searches the album and finds out Charles Mingus performed it. It searches Mingus and finds out he is from Arizona.
Okay, doing well so far.
But then, around turn 4, it completely loses the plot. Its context window is getting full of text about jazz and Arizona geography. It starts generating searches for IndyCar Arizona and retrieves a bunch of irrelevant historical races.
No.
It completely forgets that it needs to establish the largest city in Arizona first. By turn 15, it's just wildly researching irrelevant Grand Prix results, and at turn 20, it times out. Total failure.
It experienced both context dilution and information paralysis simultaneously. It lost the thread of the multi-step logic, and it couldn't stop searching for variations of the wrong keyword.
Now contrast that exact same prompt with SLEUTH.
SLEUTH breaks down methodically into its open questions section. Question 1. Who performed the album? It searches, gets Charles Mingus, and moves that to confirmed facts.
Right.
Question 2. What state is he from? It searches, finds Arizona, logs it as a confirmed fact.
Right.
Question 3. What is the largest city in Arizona? It searches, gets Phoenix, confirmed fact.
It's just marching down the list.
Exactly. And finally, question 4. Who is the IndyCar race winner in Phoenix? It searches, gets the Desert Diamond Grand Prix, and finds Mario Andretti. It solves this incredibly convoluted 4-hop question in just 11 turns with 15 precise tool calls.
It is entirely methodical, it doesn't guess, and it doesn't fall into verification loops. Because it explicitly tracks what is resolved in the facts section and what remains open in the questions section, it simply walks down the logical chain until it hits the final answer.
And that leads to, I think, the most revealing statistic in the entire paper, the GLM-5 revelation.
Yes, this is the data point that fundamentally shifts how we should be evaluating AI models.
So what does this all mean? The researchers tested the SLEUTH framework on a weaker, less capable model called GLM-5. And to make sure it followed the rules, they enforced the working memory structure with a strict runtime check.
Meaning, if the model didn't format its facts, hypotheses, and questions correctly, the system rejected it and made it format its notes again. They forced the weaker model to adhere perfectly to the structured protocol, not allowing it to cut corners.
When they did that, this weaker model recovered up to 19 points on the hardest 4-hop problems. But here's the kicker. That weaker model, using the SLEUTH structure, actually outperformed a much stronger, much more computationally expensive model, Claude Sonnet 4.6, that was running the standard unstructured React baseline.
A weaker model with rigorous organization beat a stronger model with poor organization. The tech industry is currently obsessed with scaling up, building massive data centers, training models with trillions of parameters.
Throwing astronomical amounts of raw compute at reasoning bottlenecks.
Exactly. But this research proves that we don't always need billions more parameters. Sometimes we just need better cognitive architecture. How an agent organizes its reasoning is just as vital to its success as its raw processing capability.
It is the difference between hiring a genius who is completely disorganized and leaves crucial files all over the office floor versus hiring a solid, competent worker who uses a rigorous, methodical filing system. The organized worker will win the complex marathon every single time.
And because SLEuth is entirely done through prompting, it is highly accessible. Anyone building agentic workflows today can implement this tripartite structure: facts, hypotheses, open questions, and see immediate gains in reliability without spending millions of dollars on model fine-tuning.
Let's recap this journey for you, learner. We started by looking at how standard AI models, despite all their processing power, get completely lost in their own context windows when trying to solve multi-step problems. They drown in their own unstructured text, causing context dilution.
And they fall into a trap of endless verification known as information paralysis.
But by implementing SLEuth, giving the AI an explicit, structured working memory of monotonic facts, ranked hypotheses, and open questions, we solve the context dilution problem. And by pairing that organized epistemic state with a 70% budget nudge, we cure the information paralysis, massively scaling the AI's ability to handle complex multi-hop reasoning.
It's a brilliant, highly practical piece of research. But before we wrap up, I know you were thinking about how the mechanics of this paper apply beyond just artificial intelligence and complex coding workflows.
Oh, absolutely.
The paper's concept of the evidence sufficiency problem genuinely stuck with me. These highly logical, data-driven AI agents fall into a certainty trap where they continuously gather information to avoid making a final decision. They just keep researching to delay the uncomfortable moment of commitment.
Right.
It raises an important psychological question. How often do you do the exact same thing in your own life?
Oh, wow. I feel personally targeted by that.
Right. Think about the mechanics of your own decisions, whether you are endlessly scrolling through hundreds of product reviews before buying a simple appliance, or, over-researching a new project at work instead of just starting the messy first draft.
We all suffer from our own versions of information paralysis.
We do. So at what point in your own decision-making process do you need to trigger your own 70% nudge? At what point do you need to stop opening new browser tabs, look at the confirmed facts you already have on your mental notepad, and just commit to an answer?
That is a phenomenal thought to leave on, because the next time I walk into a room and stare at a blank wall, I'm not going to blame my raw processing power. I'm just going to realize my epistemic working memory needs a much better filing system.
Check your confirmed facts and stop over-verifying.
Thank you for taking this deep dive with us, learner. We'll catch you on the next one.